So before I start discussing the work done by Professor Bose, let me briefly introduce how Planck's hypothesis was introduced. And okay, so as you all know, that Planck's law is regarding theoretical explanation of black body radiation spectra. So a typical black body, as you know, consists of a hollow metallic cavity, as you can see here. This is surrounded by some heating arrangement, and finally there is some insulating arrangement so that one can maintain a constant temperature, or one can maintain thermal equilibrium. Okay, and in this picture, the black body radiation spectra has been plotted at four different temperatures, starting from 3000 Kelvin to all the way up to 6000 Kelvin. So, and this dashed line is what is based on the laws of classical physics. This derivation was given by Rayleigh and Jeans, and here is the formula. As you can see, uh, this prediction based upon uh, Rayleigh's law agrees with the experiment only at long wavelengths, or you can say short frequencies. Okay, and then there is complete disagreement. Particularly, this law predicts that more and more energy should be radiated at shorter wavelengths, or at high frequencies. Okay, and many researchers of that time sought theoretical explanation of the experimental results on black body radiation spectra, but with a limited success. So, among prominent contributions which we still teach to students at undergraduate level were the works of Lord Rayleigh and Wien. So, as we know, Wien's law worked well at high frequencies, while that of Rayleigh at low frequencies. Okay, so there was problem in the over the intermediate frequency range, over the intermediate frequency range. So in fact, in the year 1900, although Planck was working in the area of thermodynamics, but by I would say by a chance, Planck enters the story of black body radiation spectra in the year 1900. So what happened here is a little story, that in October 1900, German physicist Rubens happened to visit Max Planck on a social call. So during dinner, Rubens shared with Planck his experimental findings on the black body radiation, and particularly he emphasized on mismatch between his data and the Wien's law. Apparently, both Rubens and Planck were not aware of the calculation done earlier due to Lord Rayleigh. So, from that night itself, Max Planck started thinking about the problem, and you will be surprised to know that the next day itself, Max Planck came out with a formula, a theoretical formula, which agreed exactly with the experimental data over the entire frequency range. So, one can say that within a period of about 12, 14 hours, Max Planck guessed a formula, that here is a formula, and which agreed exactly with the experimental data over the entire frequency range. So in modern notation, the Planck's formula is given here. Okay, here E nu T d nu represents the radiation energy density emitted uh, in the frequency interval nu and nu plus d nu. Okay, so so today we will say that Planck had just stumbled on the correct formula, but the problem was to deduce it or to derive it by using the first principles. Okay, so in fact, the problem was not solved, but the problem had started, because the main problem was to derive his formula for the black body radiation spectra using the fundamental principles of physics. And uh, after working for about 3 months, he arrived at the conclusion that there is no way to obtain this formula using the existing laws of physics. And in December 1900, Planck proposed a derivation by introducing two revolutionary postulates. And the first postulate, he said that today we will say that there are material oscillators in the cavity wall, and and an oscillator of frequency nu transfers its energy to a radiation mode in the cavity of the same frequency. Okay, and these material oscillators can have certain energies given by the expression n times h nu, where n is an integer including the value 0. That is, if I go back to the schematic representation of black body, so we would say that Planck visualized that there are material oscillators here in the walls of the cavity, and there are number as many. Today we would say there are as many oscillators as the number of atoms. So and so so let us focus on an oscillator of frequency nu. So Planck said that this oscillator, which is oscillating at frequency nu, this feeds energy to the electromagnetic radiation mode of the same frequency which exists here. Okay, and secondly, he said that the energy of this oscillator is quantized, and the expression is nh nu. Okay, so these quantized energy levels are shown here. That is, the lowest allowed energy is 0, according to Planck's hypothesis. Then other allowed energies are h nu, 2h nu, 3h nu, and so on. And Planck also argued that this assumption of discrete energy was absolutely necessary in arriving at the correct result. So this was purely a new result in physics. It may not seem so today because we are so customized to the notion of quantization today, but it was purely a new result in physics at that time, as before 1900, nobody had ever thought of discontinuous energy. In fact, you leave aside energy. So the belief was that all dynamical quantities like energy, momentum, position, all these have continuous values. So in that sense, this hypothesis by Planck was absolutely new. Okay, so in this way, you see, Max Planck was able to explain the black body radiation spectra. So Einstein, uh, in the year 1905, Einstein enters this story, and he was impressed with the work of Planck, but he was not fully satisfied. Therefore, he decided to examine the idea of discrete energy. So, in this process, Einstein argued, let me again go back to the schematic representation of black body. Einstein argued that on the basis of what Planck had said that when a Planck had said that when this material oscillator makes transition from higher energy state to lower energy state, so the energy which is emitted, that is given to an electromagnetic radiation of the same frequency. So at this point, Einstein gave his argument. He said that electromagnetic radiation receives energy from from a material oscillator in the form of a discrete or a specific unit of energy. So he said that the electromagnetic radiation carries this energy in the same form in which it receives from the material oscillator. So earlier, Max Planck had treated the electromagnetic radiation inside the cavity by looking it as a wave. You see, and here Einstein says that that electromagnetic radiation carries energy in the same form in which it receives from a material oscillator. So in this way, Einstein introduced a new picture of electromagnetic radiation. According to that picture, an electromagnetic radiation of frequency nu can be looked upon or can be visualized as a narrow stream of discrete and identical units of or packets of energy, and which he called as radiation quanta. Much later, these radiation quanta were named as photons of today. Okay, so using this picture of this quantized picture of electromagnetic radiation, Einstein not only explained the photoelectric effect, but he also provided an alternative derivation of the Planck's formula. So here is the picture which I was talking of. That suppose we have an oscillator and it is in the second excited state. So when it makes transition to a lower energy state, here the first excited state. So in this process, a radiation quantum which has energy h nu that is emitted. So one radiation quantum is emitted. On the other hand, if the oscillator makes transition from second excited state to ground state, so in this process, two radiation quanta or two photons are emitted. Here I must note that only the energy is quantized, not the frequency. Frequency is continuous. That is, we have large number of material oscillators, and they are oscillating over a range of frequencies, and this frequency is continuous. Only the energy is discrete. And okay, so there was a lot of opposition to the idea of radiation quanta, and this quantum picture of radiation remained doubtful for about 18 years. The reason was that the Maxwell's theory of electromagnetic radiation was so successful that nobody wanted to give it up. And most of the people, like Niels Bohr, Lorentz, Max Planck himself, doubted the idea of radiation quanta. However, all doubts disappeared in the year 1923 when Compton uh, demonstrated experimentally the particle-like characteristics of the radiation quantum. So so it was experimentally demonstrated that the radiation quanta introduced by Albert Einstein actually have particle-like characteristics. So the existence of radiation quanta was confirmed experimentally. So therefore, there was no alternative left but to accept the idea of radiation quanta. But at the same time, there was strong experimental evidence that electromagnetic radiation has wave-like properties. So there was no alternative but to accept. बिल्कुल है लेकिन अभी नहीं दिखा पाएंगे जा रहे सॉरी किसी का माइक्रोफोन ऑन है इसको ऑफ कर लें So there was no alternative but to accept the dual character of electromagnetic radiation as a law of nature. So in the year 1924, I think with much of theoretical background, some disturbance. ये किसी का माइक्रोफोन ऑन है इसको ऑफ कर लें
तुमने कॉपी पेपर क्यों नहीं किया था